going to quickly go over the exercise I had to do this week. I'm not going to go through every single thing, but just cover what I think are the most common mistakes and the most common questions the students have when running this sort of thing. So let's go to our studio and let me show you how to run this. So this is basically what you should have at the beginning. Remember to have your caret package installed and your model R function package installed. And let's just load our data. We're going to just drop some of the variables so we don't have any issues. So as you can see here, we have 17 variables. First question is very straightforward. It's just transform your response variable into a binary one. Again, not gonna go too much through that. I am going to stop a little bit on this line of code right here. So the main idea of this line of code is to transform any variable that is a string variable or a character variable, as R calls them, to factor variables. What are factor variables? Factor variables are categorical variables. This is how R handles categorical variables. The main idea is that you should think about them as numeric variables that have a label attached to it. With factor variables, R actually knows how to handle them, so it's very important to transform them so we don't run into issues when we run certain models. So if we look at our data right here, you can see that a bunch of these variables are read as character variables or string variables. That will be a problem with certain models, so we want to transform them and be very explicit about these being actually categorical variables. So let's run this line of code. And as you can see, all the character variables now are actually factors. So what mutate if is doing is saying identify every variable that was a character variable and transform it to a factor. So now we don't actually have character variables, we just have factors. If we look at the data, for us at least, it looks exactly the same. But believe me, something changed. These are now considered categorical variables, so that's why we want it, okay? Great. Let's move on to the third question. The third question basically is asking you to just split your data into a 75%, 25% split and create a training dataset and a testing dataset. How do we do that? First thing, always set your seed. This will make your split the same every time that you run it, so that's important. So if I run it, for instance, in my computer, I'm going to get the same results as you do. The second thing that we need is basically know how much data we have. So in this case, as you can see here, we have 9,134 observations. So if we use the function nrow, that is basically the number that is saving right there. And then out of those over 9,000 rows, what we want to do is randomly select 75% of those rows, and those will be our training data set, and randomly select again the rest of the 25% is going to be our testing data set. So let me just quickly see how many should be on our training data set. So let me multiply n by 0.75. That gives me 6,850. So I should have on my training data set 6,850 observations. So let's randomly select again 6,850 rows out of the over 9,000. So this is what we get right here. So train now is going to be a vector that goes from 1 to 6,850. That is the length. Okay, and randomly selects different rows. So for instance, the first row that I randomly selected was the 3,786. Then I randomly selected the 503, and so forth. Okay. Once that we have the rows that will go into our training data set, what we need to do is slice our data. This basically means just keep those rows that are on a training data set and transform that into the training data. And for the testing data set, do the opposite. Drop the rows that are included in the training data set. So that will be our testing data set. So if we do that, you can see that the training data is the same as the marketing data. It has 16 variables. However, it only has 6,850 observations, the number that we thought we would get, okay? And the rest is going to go to the testing data set. So as you can see, we have 2,284. If you add these two numbers, you're going to get the entire data set for marketing. Awesome. So let's move on to the fourth question. So in the fourth question, you just need to run a linear regression using all covariates as predictors. So very straightforward. This is run just as a linear model. Remember that we always train our model in our training data set, and we test the accuracy on the testing data set. Okay, so we're going to run LM on the training data, as you can see right here, and we're going to test the RMSE on the testing data set. So how do we include a model that has every covariate that we have in our data set? As you can see, we have 16 variables right here. We are not going to include response, so that's why I do a minus response, so it's not considered actually a covariate. I'm using a customer lifetime value as the outcome, so that again is not going to be a covariate. But if I don't want to actually manually type the other 14 variables, which again seems very inefficient, what I can do actually is just add a dot. So let's take this out for a second. If I just run this model right here, it's basically saying take customer lifetime value as the outcome, and everything else that is in the data set, use it as a covariate. So that's what the dot stands for. It stands for every other variable in the data set, that again, that is not the outcome, and include it as a covariate. So that is great. That's what we want, but remember that we don't want to include response, because response is going to be an outcome. We're going to use it next class when we talk about binary outcomes. But for now, we're just not going to use it as a predictor. So in that sense, we just need to do minus and whatever variable we want to exclude. If we had another variable that we wanted to exclude, for instance, if we had an ID variable, you could do minus ID. That's absolutely fine. Awesome. So now we have this. We run this model in our training data set. That will give us the beta coefficients for our model. And we're going to test how accurate our model is using the testing data set. So this is basically the RMSE that we get on our testing data set, 6,241. There's nothing random here. The random part happened when we split our data into our training and our testing data set. So there's no need to set a seed right here, okay? Just in case. Anytime that I run it, I will always get the same number. Great. Now let's move on to the fifth question. Now this is telling us to not use necessarily the one split that we used for training and testing, but to use cross-validation in order to get our results. So the idea here is that we're running one fixed model, okay, a model with all the covariates in our data set, but we just don't want to use one training and one testing data set, but we want to use the entire data at some point, both as testing and training, okay? So that's why we do cross-validation. So for cross-validation, we are dividing randomly our data into, in this case, 5 different folds. So we are going to have to set the seed in this case, so our results are replicable. If you're not entirely sure how to do this or why this works this way, go watch the other video that I made about how setting seed works. Great, so we need to tell R what method we want to use. So in this case, we're using cross-validation, that is the method CV. And we want to tell R also how many folds we're going to use. I'm asking for a 5-fold cross-validation, so that's why number is 5. If I was asking for a 10-fold cross-validation, you would use number equal 10. Let's leave it at 5 for now. And to do cross-validation, we're going to use the train function in the caret package. And we're going to fit, again, the exactly same formula that we had before. So this is basically the same thing that we had up here, which is included as the formula right here. Our outcome is the same. We're using all the covariates minus response. The data now is going to be the entire marketing data set. Why? Because we're using cross-validation. So really, we don't need the training and testing data set that we did before. In this case, it's going to take the entire marketing data set, it's going to split it in 5 different buckets, and for each iteration, it's going to use 1 bucket for testing and the other 4 for training. The method in this case is just a linear model, just like we were running before. And again, I need to say that this is doing a cross-validation, so we're providing the train control function. Let's run this thing and let's see what we get. So as you can see, we get 6,294.8. This is a little bit higher to what we got before. That's absolutely fine. This probably is still a better measure of how accurate the model is, because again, it doesn't rely on just one specific split of the data, but it actually does this 5 times and takes an average of all those RMSEs. Let's move finally to the last question, which is just to run a forward stepwise selection model. So far we've been running a model with all the different covariates. The problem with that, remember, is that a more complex model is usually also higher variance. It is lower bias, but the high variance might not compensate. The low bias, might not compensate for that high variance. So we want to know whether it would maybe be better to run a smaller model, a more restrictive model, and maybe get a better accuracy. How do we do that? We will run a forward stepwise selection model. For that, we're going to use the method leap forward. You might need to install the package leaps in this case. See if you get an error, see what it's telling you. We're going to use, again, the same formula that we had before. We're going to include all covariates. We're going to be basically including one covariate at a time as the method moves forward. We're going to do this in our training data set because now we actually need to identify an additional parameter, which we call a tuning parameter. What is that tuning parameter? This right here. The number of variables that are going to be included in our model. So beyond just estimating beta coefficients for the linear model, we need another, what you call a hyperparameter or a tuning parameter that is going to determine how many variables we're going to include actually in the model. So because of that, anytime that we include TuneGrid, for example, in our training data, in our train function, we should run this in our training data set. We're also running a cross-validation, so that's what we're going to do. Okay, let me talk very briefly on how we identify how many variables we have as a maximum number of variables, okay? So this is going from 1 to n bars. So what is n bars exactly? N bars is the maximum number of variables that is included in the model when I use every variable that I have in my data set as a covariate. So let's look here. We have actually 16 variables. One is an outcome, okay? So at most we would have 15 variables that are covariates, but we're not using response. So you might be tempted to say, okay, I have 14 covariates in my data. However, that's not really the case. If we look, for instance, at coverage, for instance, or at education, you can see that these are factor variables. Factor variables, if they have more than 2 levels, actually count for more than one covariate. They count for whatever number of levels they have minus 1. So for example, coverage has 3 levels. That actually enters the model as 2 different variables. Education has 5 levels, so that means that it enters the model as 4 different variables. We can see that, for example, if we look at the coefficients of our previous model that we fit before. So we can see here that we have the intercept, then we have coverage, we have the extended category, and we have coverage, the premium category. Again, it has 3 levels, it enters as 2 variables. Education had 5 different levels, so it will enter as 4 different variables. You can see that it has education college, education doctor, education high school or below, and education master. So it's not just as simple as just counting the number of variables that you see in your data set, because you need to count factors as more than one variable. How can we do that? I'm not doing manually because, again, it's just very non-efficient. One way that we could do it is that if we run, for example, a model prior with the entire data set, like with the entire covariates that we did before, so this is LM, CLV, CV, we can just use the coefficient names and take the length of that to see what the number of variables it is that we have. So let me just run that. And as you can see, we have 28 different variables. What we could also do, for example, let's go back here to the just simple linear model that we had. Let me copy this and paste it right here. Remember that when we run a linear model, you could get the coefficients for the model. So as you can see here, we have all the coefficients. What we could do is just do length of the coefficients. That will give you all the coefficients that you have here. We do have the intercept though, so we could do -1. and that could be our n vars. Let me just show you first how many we have. We have 28, which is the exact same number that we had before. So we could do n vars equals the length of the coefficients of the linear model, including everything, minus the intercept, because remember the intercept is not really a covariant, okay? So either of these two ways work great. So if you're not sure how many variables you have, just run a simple linear model with all the covariates, again, including dot, every covariate that you have, okay? And then just take the length of the coefficients and just subtract 1. That will give you the number of the coefficients. So we're ready to do this. Let's run this whole thing again. And let's see what we get. So first, we want to know what is the best number of covariates that we should include. For that, we will take our LM forward object that we just trained, and we're going to do $sign best tune. That will tell me that the best number of covariates that we should include is 8. And again, we can see the whole thing here. Just looking at the different models that with your RMSE, you can see actually that the one that here at 8 is the one with the lowest RMSE. So everything below 8 and everything above 8 actually has a high RMSE. So that's why that is the optimal one. We could also, for example, look at the coefficients for that optimal model. So you can see here that these are the 8 covariates that it's choosing. It's choosing education, high, employment status, marital status, monthly premium, and so forth. And you can see the coefficients. And finally, most importantly, now that we've actually trained them all, we know how many covariates we need. Let's get the RMSE. And you can see that the RMSE is 6,237, which is actually a little bit lower than the RMSE that we got from cross-validation, and even lower than the RMSE that we got just running, again, the entire model. So just remember that not always a more complex model is better. Sometimes you do need to drop some variables or exclude some variables in order to get to that sweet spot between bias and variance. And this is a good example of that. So let me know if you have any questions. I'll be happy to help you out with that, and I will see you in class.